Okay, so I suppose there are no doubts, but I see that there are only very few submissions on the second assignments. So why rest of you are not submitting? What is the reason?
Sir, can we submit by tomorrow? That tomorrow is Sunday, so can we submit by tomorrow?
Yeah, that is fine, but have you done this or like you don't,
Yeah.
only one day will not
No,
matter?
no.
Huh, huh.
I have completed 4 or 5 questions. Two or three questions are left, so that's why I'm just want one more day.
Okay,
I will
okay,
try
yeah.
to finish it by 12 o'clock today. But
No, no, that is fine. You take
just
tomorrow
give me.
also. Yeah, you take tomorrow
Yeah.
also, but complete it. Huh? Okay, okay. Anybody else? Okay, so if not, so we'll start today's class. And okay, okay. So last week we have gone through the switches, different kind of switching circuits, starting from pin diodes and FET switches. And we saw that there are various applications on steerable antennas, and mainly based on the beam forming or beam steering antennas, where you can have an antenna array and giving different phase excitation to these different antenna elements. It can generate a maximum or null at different directions. Okay, so that was the one important use of the phase shifters, right? So they are used in phased arrays. So now, even we have looked into different architectures. There are like analog or digital beamformers, and there are like hybrid beamformers altogether. So those are different things, and there are this was the whole block diagram of different uh, components in a phased array system. Okay, so now that it is understood that phase shifter is a vital component in this kind of systems. So what it actually does? So basically, you can have a variable phase control there. So which this you can vary using the voltage control. So why this voltage control are required is because of to control the switching elements. Like by changing the bias current or bias voltage, you can change the diodes or other kind of switches, and that will give you a variable phase shift. Let's see if you have multiple paths. So by choosing one of these paths, you can change the phase. Okay, so if you see the system here, the input is having a phase of phi 1 and the RF phase is phi 2, so which is given by input phase plus minus a del phi. So this del phi is the phase shift which is controlled by the V control, right? So that means this is controllable, or rather electronically controllable system. Okay. So now, as you know, the matrix for characterization is again same. We have insertion loss, which gives as the amplitude of S21, and we have return loss that gives is calculated from the S11. So using that you calculate generally, and we have a phase figure of merit, which is generally phase shift divided by insertion loss for this kind of phase shifters, right? So now the very basic phase shifters is called switched line phase shifters. Switched line means there are multiple lines. By switching between these different lines, you can have a different phase shift. So why the phase shift comes? Because of the line lengths are different. Okay, so we choose or we design these lines such a way that here if you see the one line is very straightforward and the signal goes through it. In the other way, it has a bend which has a extra del L by 2 length. Okay, so now if we design such that this extra del length is, let's say, the phase we want. So generally how is the phase calculated? It will be though obviously 2 pi by lambda into your length, right? So if you calculate that way, y- so the length, if you design such a way that you need the uh, amount of phase, okay, it will be correlated between with this equation, simple 2 pi by lambda, right? So this way you can just, switch between these lines and generate a phase shift. But now you see in the left and right side you have a
He,
SPDT switch. Okay.
he,
So
hello.
yeah, yes,
He
yes.
said delta L is the what is this delta L means here?
If you see in the
Peak power,
picture,
peak power.
no, 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 nothing related to power here. It's the
It's the
length
length
of
of
this.
the cable, length of the that RF cable.
I don't know if you are seeing the picture here in schematic. It is shown delta L by 2, right? Do you see the
Ah,
picture
yeah.
here?
Ah, yeah,
Yeah,
yeah.
right, right.
What is this? How it this? What is this wave? I didn't understand actually.
So see, you understand that there are two lines, okay? By
Um,
using switches here in the left and right side, you can select either the top line or either the bottom line. So now if we design this line such a way, they have a change
okay.
in, they have a shift in their line length, okay? So here del L by 2 this side and that side. So total you have a delta L by 2 extra length compared to the bottom line. Okay. So because of this delta L extra length, you will have a extra phase shift that is given by 2 pi by lambda into delta L. So that is how by selecting one of these lines, either top one or bottom one, you will have a phase shift of del phi. That is why it's
He,
called a phase shifter.
here the phase shift of sine and cos also is possible with this formula. Phase shift.
Phase shift is calculated through radians, right? Angles.
Ah,
So there
yeah,
is
but
nothing called sine theta. I don't understand what you're asking.
if you take two mixers,
Mm-hmm.
okay, 90 degrees phase shift, then we will get the LO and RF. Then after two outputs will come, that is the sine and cos. If the sine and cos is the two enter into the two delay lines, that is the these are only lambda L by 2 like that you are telling na.
See, let's say your signal
How
is
can we tell that a phase
cos.
shift?
No, no, I
Yeah.
am saying let's say your signal is signal is cos omega t. Okay, omega is your carrier frequency. Let's say 1 gigahertz. Okay. So
Okay.
now the time the signal goes through this extra length and comes back here, it will be cos omega t plus del phi. Okay, this extra length will come. Now, if the moment if you choose the del phi to be pi by 2, then cos omega t will become sin omega t, obviously.
Okay.
Yeah. Okay. So now how do you design these switches? That is the main problem here. So this is you need two SPDT switches. One is at the left hand, another is the right hand. So just for a one single phase shifter, you need two SPDT switch, and one SPDT switch needs two diodes. So that is why you need total four diodes here just to have a single phase shifter. Okay, that is what you should remember. Now you see what kind of different variation we can bring here. So not always we need only one variation, right? So if you see here, you just have either one phase or another phase. That means you have only two variations. That is why it's called a one bit phase shifter. Right, but not often we need a only one bit phase shifter. Generally, if you see a phased array circuit and all, we use a 8-bit phase shifter to 6-bit phase shifter or a 11-bit phase shifter. That means we need a lot of variation in the phase, right? Then only it will be very useful. So for that, what we need? We need to cascade a lot of phase shifters like this. So when you need this, though obviously the circuit becomes complexity increases, and you need a lot of diodes, you need a lot of biasing circuits. Those are required. So that is what all about the phase shifter circuit. Here, if you see here, you have one 45-degree circuit phase shifter, one 90-degree phase shifter, another 180-degree phase shifter connected together. So now and each one of them has two SPDT switches. That means four diodes. So the red ones are it means the SPDT switches. So total in this circuit you have, so 3 into 4, that means 12 diodes. And by taking three different combinations, you can generate how many total phase shift combinations. If you select these diodes here and there, total will be 3C2, combination of 3 out of 2. Okay. So 3C2 means why? Because each one you can have two combination. So total, if you will have um, a total 3 C2 means three total 6 defined combinations you will have out of this. Okay. So that is what happens, that out of this you can have either 45-degree or 45 plus 90-degree or all together. So by having more circuits in cascade like this, you can go up to as much as you want. So you have to just add circuits in series. Okay. So that way you can generate 5 or 6 bit phase shifters. Okay. And let's say for a beam steering, you need the array factor, right? Array factor is the KD cos theta plus beta. So you need a beta phase shift. So to have this kind of phase shift, you need to generate a phase shifter circuit like this. So you have to carefully see how much length you need. So the main thing is not about the length, because microstrip line you can add extra length, but you have to always see they have, each one of them has 4 diodes, and they come with lot of biasing circuits. So this is obviously as simple as looks here is not actually, if you see. Okay. So we have previously have seen, and even I have shared a document with you. If you do yourself, you will see even also a single diode switch will have so much circuits and all. Okay. So yeah, that is about it. And
Excuse me, sir.
yes.
Shall I share my screen once? Actually, I have a doubt with like this only. Is this
Mm-hmm.
concept same with, is it related to this concept also? I don't know.
Mm-hmm. No,
Once
no,
I
no,
will
you don't
share.
have to share. No, 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 don't share. You tell me what are you talking about.
That is actually one mixer is there like that
No.
only.
Okay. Yeah.
If
No, no, not one mixer. What mixer does? What do you do? It does mixing, right? You two different oscillations or different sinusoids
okay, if
and
two
mixes and
mixers
generates. It's not a phase shifter. Yeah.
here two mixers are there. So once two mixers are there.
Hmm.
If you will go to the if we give input to the two RFs,
Mm-hmm.
then the immediate frequency will get no sir I and Q.
Mm-hmm. Yes.
Yes, LO is the our okay normal port only.
Mm-hmm.
It is the 90 degrees coupler. It is giving to 90 degrees coupler. Then I
Mm-hmm.
and Q is getting out no sir.
Here, nothing. It has nothing to do with I on Q. Nothing. It is only simple RF signal you are giving. Okay. You can use it in different I and Q, whatever you want, but it has nothing to do with that. Did you see the applications before? What I have talked about phased array circuit. We are talking all these things with respect to phase shifters, right? And phase, which is used in phased array. So, you tell me, where do you see mixers in phased array?
Actually, one concept I saw sir. That's why I'm asking. Actually,
Mm-hmm.
same concept.
Yeah.
It
Mm-hmm.
is applicable or not? I don't know. Just I will share in chart once check sir.
Okay. 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 Share. Yes. Are you trying to share your screen? Hello?
Yes, sir, I'm sharing. I'm sharing, sir.
Yeah, do it quickly. Yes.
Once, is it possible to visible? Is it visible, sir?
No, no,
Full
not yet. Yeah, now it's here.
full screen. Screen. Okay. Is it?
Yeah, yeah, yeah. Now it's visible. Yes.
This is C sir. Once here C sir.
Okay,
I
okay.
and Q.
Hmm. Okay.
If it is there like this that you saw no sir one mixer here.
Yes, yes. I understand. Yes,
That
yes.
is here only, sir. If
Hmm,
will
hmm.
if will I give this, you told na sir once, this lines phase shift. Uh,
SPDT. Yes, yes. You have
uh,
switch. This is PD3, PD1. This is phase. What is PD?
what is the speed power dividers?
Power divide. Okay, okay,
Uh,
okay. So
if I
go to the previous one, previous slide.
sorry,
No, 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 not slide. You are showing some.
this one.
Yes, yes. See, the generally what mixers do. Mixers generate defined frequency signals. Okay, not
Yes.
phase.
Uh,
So if you generate a mix sine and cos together, so you will have generally not sine and cos. We take the carrier signal and we have some lower frequency signal like I and Q. So at
uh,
the output you will have omega c plus omega n and omega c minus omega n. Okay. So plus
okay.
minus carrier frequency shift you will get. Okay. But not phase shift. But here if you get what you see is frequency is fixed. Only phase of the carrier signal is get shifted. Okay.
Oh,
So
okay.
yeah, that is quite different from here. Okay, so there is no I and Q here. I and Q comes in the communication systems. Okay, we are talking
Okay.
about phased array system. There we don't want frequency shift. Frequency is fixed all way. Okay, okay. So I will
Okay.
again go back to my thing. So now there are very different types of phase shifters. The one we have talked about is called switched line phase shifters because we switch between different lines. Okay. But there are other types like this one here at the top right side is called reflection type. So here what happens, you have a power divider, power coupler or different type of network, and by having diodes or switches you can change the reflection coming out of this port, and you can here generate a phase shift here also. And there are other lines like this one is particularly they call important, they call loaded line phase shifters. So instead of using multiple lines, they have one single microstrip line, and they have loadings, multiple loadings, like multiple diodes or other lines connected in between. By varying the connections of these lines, you can generate phase shift. Okay. Another type is high pass, low pass phase shifter. So these are the different types, and they have advantages and disadvantages in terms of more isolation. Some has more reflection. Some of the cases like you can do with less number of diodes. Okay, so these are very different types. You can look into these different types. Okay, but very basic circuit here that is very quite popular and it works. Okay, so that is about the phase shifter. And they even we have even different type of implementation like MEMS implementation and even ferrite rod implementation. Those are might be very miniaturized circuits and all works in different conditions and all. So those applications are there. The you can design with different type of circuits and all. So MEMS switches are this is the one type of distributed phase shifter which are used by MEMS bridges and all, but they have their own constraints and all. Based on your requirement, generally people see which type to use. Okay. So yeah, so now that those are about the phase shifters. Now there is another component we will look into, like shortly, like not in great depth, but it is a coming kind of like very emerging topic nowadays in in microwave domain, which is FSS or metasurface, right? So we have done some work in this domain, our group. So we'll share that with you. So many of the works currently, many of the normal or conventional lines like microstrip line based circuits can be done with metasurface or FSS. Okay. So FSS is nothing but the frequency selecting surface, and similarly metasurface is made of multiple unit cells. Those are quite similar, and there are multiple applications because many times you can have you can bring out multiple applications together with this kind of surfaces, and even you can attach diodes or define the switching elements there on the surface that will make it reconfigurable meta surface, right? So one application we have lately seen was a particular type of modulation. Okay, so if generally, if you are working with defined communication schemes, if you see the last 10 or 20 years, there has been a lot of talk on RIS or IRS, like reflective intelligence screen or intelligent, intelligent reconfigurable screen like that. Okay, surface. So basically, why they are very popular? Because you can actually using these surfaces and by having reconfigurable elements, you can vary the electromagnetic propagation environment itself. So what happens? The generally wave passes through the environment and is received at the receiver. So normal traditional communication schemes, modulation schemes like let's say QPSK, QAM, and all this, generally we generate the modulation at the transmitter itself. Okay, we have this modulator and the mixer and all, they generate it and the IQ signals are passed through, but the environment itself, it is not taken care there. The environment will have some effect, like it will have some fading or it will have multipath effects. Those are generally balanced at the receiver, or the effects are cancelled in the through signal processing mainly, and then we receive at the receiver end. But what lately people are talking about in the communication paradigm is that even the environment itself can be reconfigured, or by having a these innovative hardwares, we can generate different combinations by generating different modulation schemes, so that will be useful. So few examples are like spatial modulation, and there is SSK or space shift keying. Okay, and there we have even MBM or media based modulation. So these are the new topics or new different type of modulation screen effects. So what happens that like generally in SSK or space shift keying, you can have multiple antennas there itself. Okay, so multiple antenna, or let's say multiple type of meta surface or FSS, and by selecting one of them or a combination of them, you can transmit. At the receiver side, you will receive something. Okay, so if the receiver can detect based on the signal strength, signal amplitude on phase at the receiver side, receiver will know from which combination of the antennas at the transmit side it came. That will provide additional information. Okay, so that is why it's called space shift keying. Why space? Because the antenna, all those are distributed in space. Similarly, another modulation scheme is spatial modulation. So spatial modulation is also similar, where we have the normal communication scheme like QAM, QPSK in combination with this SSK, shift keying. So together they bring a spatial modulation scheme. So you use a combination of multiple antennas to transmit along with your signal QPSK or QAM. So that will bring additional information at the receiver. Okay. So that is one. And the other topic we have studied in particularly in our lab, our group, is called MBM or media based modulation. So what happens? Why media based modulation? Media is nothing but the environment through what the wave propagates. And by changing the media itself or taking advantage of the propagation through the medium itself, we create the received signal or our received constellation at the receiver. That's why it's called media based modulation. So how does it work? So let's say here we have a screen here. So this screen can be any type of screen. It's like it can be a can be a meta surface. It can be a screen of like thousand and different patch antennas, all controllable through some switches. Okay, or some space shifters. So we have a antenna and we have a receiver at some other site. Okay. So just by changing the screen conditions, so the condition is the screen has to be reconfigurable. It has connection with multiple diodes or switches. So by changing the defined conditions in the screen, the signal passes through the screen and goes through the environment or the media in between the channel will be different, because obviously it acts like a window, right? If you just close and open the window, that will ensure how much signal goes from the transmitter to the receiver. Okay, now at the receiver, if you just record these signals for defined combinations of the screen, it will give you a constellation or a signal set that you can use for your code book for your signal transmission. Okay, just like you have a alphabet or code book in the normal QAM or QPSK, here also your code book will contain all these defined signal sets. So these signal sets will be generated by the defined variations in the screen. Okay, the screen is a reconfigurable screen. If you change this by multiple switches and all, so they will generate these combinations or states. Now, because the environment here is scatter rich, what happens? Because scattering happens because of defined, objects in the medium, the signal what you receive will be different through defined paths. General traditionally is called multipath propagation, right? Or scattered propagation. So because of that, your receiver signals will be defined for defined screenings. So yeah, this is a whole block diagram. So what it shows a transmitter antenna at the blue side, which is nothing but let's say it's a patch antenna. Okay. In front of the patch antenna, we have a meta surface or FSS, which is controllable. This yellow, green, and red things you see, those are multiple switches, which is controlled through a circuit. Okay. Now the transmitted signal by the patch antenna goes through the surface, and it goes through the channel here, and receiver finally receives it. Receiver can be a simple antenna or a horn antenna, patch antenna, anything, but the modulation happens here is generated by this surface here, okay, by switching this surface. So it has even different names. Even people call it direct antenna modulation or directional modulation. Those are different terminologies in, okay, in our microwave domain. So yeah, this work you can follow. This is by Dr. Aditya Rai from our group, and this digital reconfigurable metasurface array for a multipath based wireless link with media based modulation. So it has been published in 22 in IEEE Transaction on Microwave Theory. So and done through jointly through our Professor Binay and Professor Chokalingam here in EC department. If you are interested, you can look into this work here. Okay, so I'll suggest it's a very new work. Suggest this. I'll suggest you read go through this topic and you'll understand more. So the unit cell here, the for the meta surface is made out of like this. It looks like this, and it has a pin diode here. Each unit cell has a pin diode, and if you switch the pin diode here, so it will. If you see the S21 data, it shifts. It has a quite a good amount of shift between the two defined condition. One case pin diode on, another case pin diode off. So by switching this, you can just see in one case the S21 is close to 0 dB. In another case, the S21 is close to minus 20 dB. So that means it works like the unit cell itself works like a switch. In one case, the signal completely passes almost completely. In another case, almost blocks the signal. Okay. So if you have a array like 8 cross 8 array we have made here. So if you switch the spin diodes on the surface, it will either let the signal pass through it or either block it. Okay. So it's kind of like a filter, but it's a reconfigurable filter because we have pin diodes and all these pin diodes are controlled through a circuitry. So by changing this circuitry or diodes, it will generate different variations of the signal. All right. So this is the surface what it looks like made by Dr. Aritra again. So if see these are the unit cells and the dots here are the diodes. Okay. And here it shows the microstrip antenna at the bottom of the surface. So altogether this makes a transmitter circuit. And this is the antenna radiation for defined states. So if you see that this is the radiation pattern for all defined variations of the switches, it has quite a lot of variation in the board side itself. In the board side, if you see almost 10 dB variation between different states. So and this sets the complete flow of the circuit. So this experiment was done in our anechoic chamber in our lab. So if you see we have lot of components here. So the antenna and transmitter, they have a Arduino control circuitry here, which is controlled through a PC. and the receiver end we have a horn, and both the horn and the transmit antenna array is connected to a VNA. Okay, so by changing the switches in the circuit FSS or meta surface here through the Arduino, we can generate the combinations and the horn antenna receives the data. So by changing the diodes here, switching on and off, we generate different combination in the media. So that's why we modulate the media. That's why it's called a media based modulation. So yeah, so this is the complete chain of this. And if you are really interested, you can go into the paper, and even we have a patent also on the work. So yeah, you can go through the paper, you'll understand. And these are the defined magnitude and phase combinations for different switch of the diode. And as you vary, go to the different angular directions. If your receiver might be not only in a both side, you can be in other positions also. So the signal set it changes. Okay, by taking one of these signal sets, you can use as your code book. This is if you see 0 degree, 15 degree, 30 degree is the locations at the far field, multiple locations. So far is this part, and then we'll go to the RF energy harvesting. So before going there, do you have any doubts so far?
One small doubt, like the
Hmm.
concept, what you have presented means like in the paper and all, we can refer for better understanding.
Hmm, hmm,
So, but basically, like the screen which is implemented just right after the patch antenna,
hmm,
the
hmm, hmm.
purpose of that screen is for like any kind of improving directivity or something like.
Yeah, you can say to improve or vary the directivity. Not only directivity, we are changing
Mm.
both amplitude and phase of the signal passing through it. Okay. So for
Okay.
all defined combinations of the signal, okay, let's say we have 8 cross 8 array here.
Mm.
Okay. So it can
Yeah.
total generate 256 defined, total 256
64,
elements.
64.
And so
Yeah.
we have 64. So total combinations will be 2 to the power 64, right?
Yes. Yes.
Okay. Yeah. So by these defined combinations, each of them will have a defined amplitude, what we saw here, right? It will have
Yeah.
different gains, and it will have different phases also. So both amplitude and phase for defined combinations will be different, what the receiver sees. So that
Mm.
way, it is kind of a modulation at the RF itself. Generally, what we do modulation at the baseband, right? Normal
Mm.
modulation
Correct.
schemes.
Yes.
Here we
Yes.
are doing
Mm.
modulation at the RF itself through a defined hardware or defined circuit.
Okay. Mm.
Yeah. So if you see the carrier signal is coming as normal, we are directly connecting the carrier to the
Blue patch.
antenna here. Yeah, yeah. Then we are
Okay.
doing the modulation in the air or in the RF signal directly. Yeah.
Okay. Okay. At the RF.
Hmm,
Okay.
yeah. So what happens is, see, the advantage here compared to the other ones in the baseband circuit, if you see, so there for your normal modulation schemes, you need a lot of other components. You need a mixer as well as a filter, and all the other components are there for modulation and all. Okay. Here you don't
Mm.
need anything other than this surface itself. So circuit, so you can get rid of the mixer and other components. That is the
Okay.
advantage of this new modulation schemes.
Okay. Means like the same RF, we can even at the receiver, we can even decode that one.
Yeah,
Means like
exactly.
whatever the different, yeah, because at
Yeah,
RF level
right.
we are implementing.
Right, right, right. So this is one way, and you can. So there are many interesting uses coming out. So you can look into DAM or direct antenna modulation or even directional modulation, and there is
Okay. Okay.
SSK. All these schemes. You look into this here also. It is mentioned. Yeah. So
DAM, no? Direct antenna
DAM.
modulation.
Yeah, nice. So these are very useful combinations nowadays, and there are a lot of papers coming out
Okay.
on these topics. So look into this. It's
Okay.
very interesting.
DIM and
So
others, what you said, like the
SSK, space shift keying, and
spaceship king.
another is called SM or spatial modulation.
Okay, okay, yeah,
I will suggest you go through this paper. It is a very good MTT paper. You will have a good gist of all the topics in this related
yeah,
area.
yeah.
Hmm, hmm.
Sure, sure. Thank you.
Okay. Okay, so we'll be starting now the RF energy harvesting. So, as you see, there are a lot of RF or microwave signal in the air. It's coming from everywhere, right? Starting from the mobile towers to the Wi-Fi terminals, even from our mobile phone or all other RF terminals we have around us. It generates a lot of signals around us. So, is there any opportunity or scope to harvest those energies? So those are the the topics in RF energy harvesting, and there are other topic related topic is called WPT or wireless power transfer. Okay, so these are related topics. We'll look into that. So it talks about harvesting of ambient radiation. Ambient means which is already available in the nature, right, or the environment. So the question is obviously, is it possible to harvest, and what are the sources? What are the RF sources required? And what are the type of hardware required for this? Mainly what is required is a rectifier plus antenna together. So commonly people call them together as rectenna. Okay. So this is a rectenna circuit. Generally they provide all of them together. Rectifier plus antenna. We'll see why these different things are required. And you have requirements in terms of normal antenna as well as impedance matching. So we need a radiative transfer of energy in case of wireless power transfer, right? So energy will be transferred not by through a cable, it will be transmitted in the other end. There should be a hardware which can harvest that energy. So a very simple circuit looks like this. Okay, so here you have a antenna connected to a transmission line, and then it goes through a matching circuit and then connected through a rectifier. So and then you have a storage element. So why these are required? Because the we need a RF to DC conversion, right? What we want finally is a DC, and through antenna what we are getting is a RF signal. So definitely we need a rectifier which will convert the AC signal to DC signal. Now before that, because it's a rectifier and we have antenna here, so obviously there is a mismatch of the RF signal. Now we know unless you have a matching, we don't have signal flowing to the other end. That is why a matching network is in between. And you need a storage element, let's say like a capacitor, which will do the storage of this power so that you can use later. So applications are, so obviously RFID tags, wireless sensor network nodes, biomedical equipment, and different automation things in our the new age smart circuits or devices. Okay, so they might have very less power requirements, which can suit or which can be uh, adjusted through this kind of harvesting circuits. Okay, so now we will see one by one. See, there are like there is differences of how much power you can actually harvest. Okay, starting from RF there are a lot of different ways, like obviously solar light which has the harvesting of ambient light, so that gives you some certain uh, wattage or the how much power density can be brought here. Okay, and differently you have thermoelectric vibrational energy as well as airflow energy, and even hand generator or push buttons, all these different types are there. They generate from a watt to microwatt in all different ranges. Okay, so generally in ambient RF we get very less power, 1 microwatt per centimeter square, because generally we try to minimize the RF power, right? So obviously we cannot expect a very high power from the harvesting circuit, but still whatever we get, whatever we can achieve, we have to maximize the efficiency. That is what is kind of the requirement of these circuits. So obviously, yeah, solar is a one good source, but sometimes, as you know, solar only works when you have a direct sunlight, available. So you can have a, backup or standby RF harvesting circuit which can work at the night or different weather conditions. So that's why people say, no, it cannot be done. Maybe, harvesting may not be done only through RF, but it might be a backup or secondary source. Okay. So there have been, a lot of study from the past. So obviously the first study you can remember about, Dr. Tesla. So who is demonstrated in 1899 that wireless powering was possible, and he actually, you know, he was able to lit fluorescent lamps 40 kilometers away from the power source. You can understand it was 40 kilometers away. Okay, and that too in 1899. So and that generated multiple patents. So definitely, the study is going on from long time, but all those cases they might be, they have been used, a lot of high powers and all that might not be actually feasible. So we still have, wires for normal hours energy, AC energy supply, right? And there was like, 1960s WC Brown, he coined the term rectenna, and he used to directly convert incoming microwave to DC. Okay, so that has been already done that in 1960. He demonstrated the ability to power a helicopter solely through microwaves for 10 hours continuously. So yeah, that seems like, amazing. So so all those studies have been done obviously, and that requires large power to transmit over long distance. Obviously, so you need large power for all these different applications. So you have to transmit yourself, and then that can be harvested at the other end. But what we generally, interested in is not like we transmit a power and then harvest. We want to see what is the ambient power already available in our environment. We want to, harvest or collect that energy itself, right? So another, you know, exotic topic I will say is called SSPS. It's called Space Solar Power Satellites. So people are talking about if we can, if we go out outside Earth, we might get a good amount of solar energy all the time, right? But in the Earth, it happens we have shadow and all the things. That's why it is, and because of the Earth's environment also, the the amount we can harvest reduces through solar panels. So there are study on if we can actually harvest the energy outside through a satellite outside Earth, and then can we beam that energy to ground? Okay, then it will be quite useful. So this is one type of study based on solar panel. And there are study on near field wireless power transfer. So obviously, as we saw the Dr. Tesla and Brown study, if you want have to, have a far field transfer, then you have to actually transmit lot of energy. Lot of means in maybe megawatts of energy. So that is obviously, not possible. So people have studied, is it possible in the near field? So then what people generally see, it has been possible. There has been demonstration by MIT to transfer high power, and they used magnetic coils or resonant coils that works at the very low frequency, 100 kilohertz to a few megahertz. Okay, so obviously, what is the energy, application of this you see. Definitely, if you see that Apple phones, iPhones uses a inductive charger. Okay, so without touching only you can have a energy, I mean without a cable you can have a charger there. So this is one of the type of use there, near field wireless power transfer. Okay, so you have a cable, inductive cable. Through that, the energy gets transferred to the other device. So as you see, the efficiency here, the plot efficiency versus distance, so falls very drastically. So that is quite, understood, right? Because as you go far away from this, the energy will or the fields will digress more and more. So you will have very less energy collected at your receiver end. Okay. So that's why it's called near field wireless power transfer. And it works at the lower frequency range also. So this is the one scheme by Texas Instrument. They have a development kit called Key. Okay, so they have actually, works. They works based on this wireless power harvesting on this energy coils, the inductive coils. You can look into, their kit. Is very, interesting. So obviously, the two extremes are far field to near field, wireless power transfer. So far field you need, megawatts of power. It can go up to thousands of kilometer, and generally it works in high frequency. Okay, and you need a very bigger aperture also. Let's say kilometer to kilometer array. But in the lower end, or near field wireless power transfer, it might works in milliwatts. And but the range is obviously, it will be in millimeter to centimeter range, works in lower frequencies, and the aperture you need to harvest the energy is also less. So that is what is, commonly understood. So obviously if you want to have something more, there is a trade-off, right? So these are the, near field applications, MIT demonstration and key standard and phone charging solution like in iPhone available, and vehicles running or sensors running on wireless power. Those are the applications. So these are the, different uh, circuits already, available in the literature or in commercially available, which is used for wireless power transfer or energy harvesting. Okay. There are different circuits, starting from this first one, which is, uh, WISP, wireless identification sensing platform. And there are like, even it is used in printed RFID tags as well as sensing tags, because tags, it needs very less amount of power, and generally they works based on resonant elements, right? So if it can harvest the energy, and then it can, have a different type of, it can generate different circuit or antenna characteristics that will, make it, very easily available. So generally RFID tags, it does not can have any battery or anything. So it just have a resonance circuit and all. So it might have a it might have a harvesting circuit which will take the energy from the environment itself, and then it will work based on that. So the very, what will say, the new use or new, the first time application was um, after the MIT demonstration was this wireless identification sensor platform on 2009. Okay, so this was done through the collaboration of Intel Research Seattle and the University of Washington. It was very useful for RFID tags. Okay, so if you see, they have two long arms, that is actually one dipole antenna connected to a circuit. Okay, so this is obviously is very useful for RFID reader. Yeah, you can see, you'll go into the link and see more about this. And there are different RFID sensors separately, or even RFID reader also. So just based on the reader, the energy will be sent towards the sensor, and the energy harvesting circuit can, make use of that. So this product, yeah, is from this Power Casco company. That is one of the applications they have shown. And then there are applications for batteryless wireless terminals. Okay. So now obviously, what is the demand and supply things? The what people envisage that it will find these energy harvesting circuits will have a lot of use in future Internet of Things era. So Internet of Things is like there will be lot of devices will be connected to each another. Okay, they might be, very smart devices and will have very less power requirement. Let's say my milliwatt or microwatt range. There it is possible to have each one of them having some energy harvesting circuit, and they can, give some sensing, work for sensing or different type of applications. Okay, but currently the, the problem is obviously people are trying to work on the efficiency, energy efficiency. uh, and the other problem is definitely the storage, right? Just like all other electrical vehicles or electrical type applications, the problem is how much can you actually store, right? So obviously, it's not always possible that on demand you have a continuous supply of power, right? So we have to store the power whenever is possible. We have overflowing power, so we'll store it, and then use it later. So definitely depends on the battery availability. There are study on supercapacitor and all, but still not at the the final phases. Might take some time. So that is a bottleneck here. So now we'll go into the specific design of rectifiers. Before that, do you have any question here? So okay. So if not, so now we'll see how actually a basic the rectana or the energy harvesting circuit is designed. Okay. So as I told you, the basic components are obviously antenna. Then we have a matching circuit, then a rectifier, and then load. Right. So the obviously challenge is in the improving the power conversion efficiency. So as you know, every circuit, electrical or microwave circuit, they won't have 100% efficiency. They will have some losses here and there. So the more you can improve the efficiency, the more amount of power you can harvest at the load at this end, right? So let's say already we have very much less power available. Let's say we have minus 30 dBm power available. Okay. If you are very close to a Wi-Fi terminal, the input power you can get is around minus 30 to minus 40 dBm. Okay. So even with the small amount of power, if you don't have a good efficiency in your circuit here, harvesting circuit, the voltage what you will be having at this end will be even less. It will go to micro watts, let's say, or microvolt. But if you have a good efficiency circuit, it might go to millivolt or even a volt. 3 to 5 volt also you can get. Okay. So that is why the power conversion efficiency is a big deal, and you have to maximize it. That is the design challenge generally in this kind of circuits. So now the thing is, how do you have the conversion from RF to DC? So you need obviously a rectifier, right? So you have to generally we use a Schottky diode. Okay. So now I have a question for you. So generally, how does the rectifier works? You have a bias circuit. You provide a on the good amount of voltage. Let's say 5 volt AC volt, 5 volt peak to peak, and at the other end, you because of a half wave rectifier, you have some DC voltage, right? So now here you don't have any biasing, right? Because if you energy harvesting circuit itself, if you provide a biasing, that is like nothing, right? So it does not make sense. So how does this rectifier works? What do you think? How does this rectifier is working? Yeah. So yeah, take a guess. How does a we generally use Schottky diode? What is the advantage of that Schottky diode? Why does it act here useful here?
Maybe the capacitance at the junction of the diode
Mm.
will.
Mm. No, it does not have anything do with capacitance, right? I am saying generally what do you do in your normal circuit rectifiers, right? You have some 510 voltage AC coming out, and then you do something, and you get some DC because the half wave or full wave rectifier. So now
Yeah.
here, what do you get? It's very less voltage, right? Let's say in millivolt or nano microvolts, you are getting at the input end. So, do you think the normal diodes will work here? Why is a Schottky diode required?
Mm,
Very less forward voltage drop.
Yeah, do you think the Schottky diode has this advantage?
No, I'm trying to tell that very it's in millivolt, so it will
Huh.
not be able to. We have to boost the signal first of all.
Mm-hmm. Okay.
Then only it has to be amplified to some milliwatt to so watt or something.
No,
Then
but
you take the signal.
but see, you can't use amplifier here, right? That will again need
Yeah.
some circuit. It will need power.
Yes.
You cannot get any extra power here, additional power. So how do you think it will work then? How do you boost the energy?
So you are given in the slide itself. It's a voltage doubler. You take the signal, just boost it
Huh?
up using as a
No,
voltage
but
doubler.
the voltage doubler is at the load end after the rectifier. Okay. But in the input side, I'm saying at the input of the rectifier, how do you think it will work?
You have to do have a impedance matching,
That is
and
obviously in the picture. I mean, why does it help?
then the maximum power transfer happens.
Yeah, that is obviously see, we are looking into maximum. Yeah. So I mean, yeah, what is the other advantage? I mean, and coming back to the diode, what is the advantage of Schottky diode compared to normal PN junction diode?
Huh. The substrate is very thin, and you was explaining the last class. Okay.
No, no, nothing to do with substrate. I'm talking about the diode itself.
Diode
Yeah.
Here,
less threshold voltage to turn on.
Less threshold voltage. Yes, yes, you are going in right direction. So the thing
Yeah.
is, yeah, most of the diodes
You are,
have a good amount of cut-in voltage or barrier voltage. Okay. So
uh,
now
s-
this
s-
Schottky voltage, not every Schottky voltage even. So I will show you just shortly. I will show you a data sheet of a special type of Schottky diode. So which have the advantage of some of them have the very low cut-in voltage or barrier voltage. Okay. So in that case, even in millivolt range, it will work. It will work for as a rectifier. Only then it will work as a rectifier. Otherwise, it does not work. Normal PN junction diode, if you use here, it will not even the diode will act like not act like a switch only. Okay. So the rectification will not happen. Only that's why Schottky diode is useful here. Now the other components is obviously impedance matching is required. So that is uses because the from antenna terminal the load voltage is generally we generate it for match or generate design antennas for 50 ohm load. But the rectifier here, it might not have 50 ohm load. It generally has a complex load. If you look into the input impedance of a rectifier, it generally has a complex load. Now, how do you match a 50 ohm antenna impedance to a complex load here? So definitely you need a impedance matching network in between, which will convert this the complex load to the 50 ohm. So that's why matching as well as you need a conjugate matching. Okay, that's why the maximum power transfer happens when this matching network makes a design such that the load and the source have a conjugately matched, then only the maximum power transfer will happen, right? This is the basic circuit. And now many of the times what happens, the at the output of the rectifier the voltage might not be enough for a some specific sensor or other uses. You might use a voltage doubler again, so that will improve the signal. So that will not be a very big amplification what you get. This will be a minute improvement. So that might be useful for a small circuits like a sensors and all RFID tags. Especially if you look into the circuit now. So very simple circuit if you see. So now coming back to the thing, the application we'll see tomorrow. I will show you a tutorial, okay, on this. So and in the next assignment will also have this kind of circuit, okay. So you study this part particularly, in depth. Okay. So coming about talking about the diode, Schottky diode, you see. So this is one diode datasheet we generally use. It's called HSMS 285X series. It's from Avago Technologies or Broadcom. See what it says. Surface mount zero bias Schottky detector diodes. Okay. So it is important part is zero bias part. Okay, it does not require additional biasing. Even now, if you read here, see zero bias Schottky reactor diodes has been designed to optimize for use in small signal P in less than minus 20 dBm. Even in the very less signal, it will work. Okay, so these are actually very useful diodes, and it has a high detection sensitivity and low noise. All this comes in a various packaging also. So, generally it looks like, different packagings. In a single, you have one diode. In a series, they have in the packaging two diodes and even three, four diodes. All these combinations are available based on what you buy from the circuit market. And this data sheet, you get all these different characteristics of this. And the equivalent circuit is obviously the you have a series resistance, which is generally the lead no, series from the spice parameter you can get it, and you have capacitance and impedance together in parallel, right? But as you see in normal diode model. So these models are generally given, and you can test yourself in the ideas. And so now coming and talking about all this, the barriers. They say the height of the Schottky barrier is specially talked about here. Okay, so it says the barrier height here is in general the very low barrier height diodes are useful for zero bias applications. So they have designed the diode such a way it has a very low barrier heights. Okay. So I will suggest you guys, look into this data sheet again. The, as you know, the name is HSMS 285X series. Okay, it's very useful. Okay. Now coming back to circuit here. So simplest circuit what we can test in ADS is like, we have a input here, AC input. So which can be the SP in the range of, some gigahertz range, which has a resistance, source resistance, and the filter is done through or the matching is done through this LC network. So L is in series and C is in parallel, which is done through this, and then you have a diode for half wave rectifier, and finally it is stored at capacitance. So has a capacitive load. So obviously the matching circuit is required from 50 ohm at the antenna side to the high impedance load, the with the of the diodes, which has a capacitance and high R in parallel, right? So you have to match the antenna to this rectifying circuit. Yeah. Is anybody asking anything? Okay. Okay. So what happens? The generally this LC matching circuits not only generates gives the matching, it can even give the voltage magnification. So how that happens? Because at some point you will have a resonance. In that resonant condition, the voltage across the diode VC here at this point, if you see the circuit here, it will be amplified, multiplied by Q. Q is the Q factor of this LC circuit. Okay. So obviously, the higher the voltage across the diode, the efficiency will be increased. And even some cases that is not even more sufficient, then you might use a voltage or voltage doubler or multiplier. So simply, you can just calculate. The simple circuit is easy to calculate. The VC is V in into 1 over j omega C plus this, because this is a series circuit R, L and C, and across this you can calculate the VC diode. And at resonance of this series RLC circuit, you will have the VC. The VC formula expression becomes this, which is even simplified to Q factor of this series circuit. Okay. So if you create a resonance, it will have matching as well as some voltage magnification that will increase the efficiency. So the main design challenge, the first part will be how to design this matching circuit. Okay. Now if you see the performance, so it is like quite understood that if you go away or from this, you will have your the more the input power, the your efficiency will increase obviously. So RF to DC conversion efficiency will mainly depend on the incident RF power and load impedance. Okay. So incident RF power, if you increase, obviously you will have more efficiency improvement. If you see the bottom plot here, is the efficiency versus voltage plot. Voltage is at the load voltage. So it's, and the defined color plots are for defined input voltages. So the green one you see, it is minus 10 dBm, is the highest input power. So that's why efficiency is maximum. But the interesting thing is you are not getting both of them. You see the curve peaks at some output voltage and then it falls. So you don't get, throughout, you have to sacrifice something. If you have to get a very high voltage, there you have to, sacrifice the efficiency. That is how it works. There is a trade-off. After some point of voltage, it drops. And even there is a, so the thing is, you have to see here, the two factors are there. Not only efficiency, you have to even improve the S11 also. If the reflection itself is bad, the most of the signal will obviously get reflected from the antenna terminal itself. So then it will impact. So you have to, there are two design considerations. One is improving S11 and improving efficiency, both. Okay. So this is one type of circuit which is, taken from the book by Professor Binay and others. You can look into this book, Micro and Smart Devices and Systems. So there you will have this, particular chapter. I think you can look into this. It's taken from there. So this circuit here, see, this is actually layout implementation. Okay. So now simple LC circuit, as you know, you can implement in microstrip as well as a component. So here the capacitor has been implemented by a stub, open stub, but L has been taken a lumped element only. Why lumped element? Because it, I told you, right? We have seen this before, that it might not be always feasible to connect, have a uh, the possible replacement of lumped element, because the line might be very thin or very wide. Both of these cases we might not, possible. So you have to have a lumped component in that case. So, but you see the problem is, because on the moment you have a lumped component, you need a pad also for soldering. Those are important. And then this HSMS 285, we see the same diode what we have seen datasheet, the same series used, and there is a capacitor across it. It's a very simple circuit, but there are a lot of consideration inside. So that we'll see in tomorrow's design. Okay. And you have shown that your next assignment will also be in design this kind of circuit. So we'll study in the RF, the ADS. So what is the impact of input RF power? If you vary the RF input power, what happens with the output? How do you improve the efficiency? And what is the impact of load impedance here? If you take a capacitor or load RL resistance or a combination of this, what happens? So if you see, there is a table already for different input power, what happens for different frequencies, and across different frequencies what happens for the efficiency. Okay, so obviously, efficiency speaks at maximum input power, and there are different voltages, output voltages you get. So all are generally in millivolt. In some cases you get in some volts. Okay, it's possible when you are very close to a RF terminal, you might get in terms of volt. Like specifically if you go near to a mobile tower outside, then you can get in terms of volt also. It's possible. You can harvest that much energy also. So that was only one diode, that means half wave rectifier. Similarly, you can have two diodes to have a full wave rectifier. So obviously, you will have more power there, because you will not lose one half. You will have both the halves energy here. So again, this circuit again taken from the same book is very useful. You can look into this, and it has a table. So yeah, now do you have any question here? We are close to ending this today's session. But the simple theory is here only in this slide. Okay, it's very simple. You have a matching network, LC network, which will act like a resonant device, and then you will have maximum power transfer happening. You will have both matching, S11 matching, as well as good efficiency. You will harvest. Yes. So yeah, just go through this and you will understand. Okay, and the perspective is like, what is the energy requirement for the application, right? So why all this? Where we will be using? So there has been a table on this papers here, the referred papers. So what is the power consumption of all the different devices we can think of? So at the top we have smartphone which needs about a 1 watt power. At the bottom it comes a analog to digital converter which can work even a microwatt, right? So about so where this can be useful is like wireless sensor node. It requires around 100 microwatt to RF receiver chip, GPS chip, and again in the wristwatch and all. Okay, so you might need in several microwatt which can work. So even a pulse oximeter people have studied. It can work in a 90 microwatt power. To it has to process this data as well as it has to even transmit. Right. Generally, the things in the IoT scenario, the devices has to collect the data and then transmit to through a wireless device to a other node. Right. Then only it will be useful. So these are the defined applications. You can choose or you can design your circuit among one of these power requirements. Yeah, and for more study, you can look definitely into these papers. Tomorrow we will look into one such design. Okay, so we'll end it today here. Do you
One
have
small
any?
doubt.
Yes.
Yeah, like actually based on this like Schottky diode, we are sensing means like the low voltages also we are sensing.
Hmm.
So will it have any impact with respect to the temperature of the environment where the this application is operating? So means like I meant to say whether temperature has any impact on the this conversion.
Yeah, it might have. It obviously because in temperature, according to temperature, the diode voltage and current will change, right? That characteristics will change. So that might lead to different variation in your efficiency. Yes.
So we have to give an importance for that also while making use of the
Mm-hmm.
application
Right,
like in
right. Yes,
respect to
yes. But generally, we want to use all these things in a room environment, right? So we are not more interested in, even maybe in RF ID tags and all. It might be, yeah, it might be useful to look into that also. Yes, it will be outside. So yes.
yeah.
Mm.
Okay, thanks.
Yeah. Okay, so that's all for today then. Tomorrow again we'll meet this time. Uh, okay then. Bye. Good night. We'll meet you tomorrow again.
Bye all.
Thank you, sir.
Mm-hmm.